Welcome back to Honors Calculus. In this video, we're going to start into Lesson 3, Continuity at a Point, with the definition of a limit. Before I get into that, recall from previous algebra coursework, you've probably seen the idea of a continuous function as a function whose graph you can draw without lifting up your pen. That's a good working idea of what we mean by a continuous function. And I want you to keep that in mind as we go through the process we are looking at in the videos in this lesson. The idea is not going to change, but as we've done in several other places already in this course, our goal here is to give that idea of continuity a solid foundation, a framework in which we can very conclusively show when something is or is not a continuous function. And the building block, the basis of that definition of continuity is the idea called the limit. So let me get my head out of the way and give you the definition of a limit, which is an incredibly dense definition that's hard to follow on its own. So let's start off by letting f be a real valued function, and let's let c be any constant, any real number. The limit of f at c is denoted LIM, a nice abbreviation for limit, as x approaches c. This is the distinction between calculus and algebra. We don't want x equals c, we want x approaches c, or x is near c. But the limit as x approaches c of f of x is equal to some L if and only if, IFF, for all epsilon greater than 0. Right. First thing I want to take a break for, I've mentioned this upside down A, for all or for every or for each. This next guy is the Greek letter epsilon, just a variable. So we have this variable, this value we call epsilon. The only thing we know about it is that it is positive, it's greater than 0. By convention, we usually assume that epsilon is a very small value. So epsilon is a very small distance away from 0. Right? Upside down or backwards, capital E is there exists. Again, we've talked about that already. Then we have the Greek letter delta, again, just another variable. So for every epsilon greater than 0, there exists a delta greater than 0, or we can find a delta greater than 0. ST, again, abbreviation for such that. Then the absolute value of f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus c is less than delta. What we are really trying to say here is that f of x is close to, is approximately equal to L whenever x is approximately equal to, close to C. But with this extra 0 on the left-hand side, we want x not exactly C, right? If x was equal to C, the absolute value of x minus C is 0. So we put 0 is strictly less than this absolute value to insist that that can't happen. So our goal here, what we are looking for in this is x is really close to C and f of x is really close to L. This is a very cumbersome way of setting up this idea of close to, but it is the foundation of all of the branch of mathematics called analysis. Calculus, real analysis, the analysis of real valued functions, numerical analysis, the analysis of computers and approximations of computations, right? How close can a computer get to performing a computation on particularly large or cumbersome numbers without having to round? And it turns out that this fudge factor that this definition of limit gives us really allows us to do a lot of things that are impossible in just algebra. All right. So let's take a look at a particular function, 5x minus 9. This is a linear function. It's a very easy to work with function. And you know from previous math courses that linear functions are always continuous. They are always very well behaved. If there is any property that you want a function to have that would make the function nice, you can almost be assured that a linear function has that nice property. So if I evaluate, plug in x equals 4, 5 times 4 is 20, 20 minus 9 is 11. So it seems very reasonable that the value of this function is, or the value of this limit is 11 as x approaches 4. The definition of a limit says that we can do this for any value of epsilon greater than 0, and in fact for every value of epsilon greater than 0. For right now, let's look at one particular value of epsilon, specifically 0.001, relatively small number. You can think of this as do some calculations and round your answer to the nearest hundredth. How close do we have to round the value of x so that when we perform the calculation, rounded to the nearest hundredth, the result is 11? Well, the definition of a limit says we want the limit of 5x minus 9 minus 11 to be less than epsilon 0.001. Right? Combining some like terms, 5x minus 9 minus 11 is 5x minus 20. And I can factor out a 5. So if I divide both sides of this equation by 5, I get that the absolute value of 5x minus 4 has to be less than 0.0002. And remember that the definition of limits said that if we pick an epsilon, we can find a delta so that whenever absolute value of x minus c, in this case, absolute value of x minus 4, is less than that delta, then absolute value of f of x minus L is less than epsilon. So we started with, well, what will it take for f of x minus L to be less than the value of epsilon we picked? We did some arithmetic, some algebra. We found that absolute value of x minus 4 has to be less than 0.0002. So if we pick delta equals 0.0002, we can be assured that the definition of limit will be held up. We could pick something smaller if we wanted. Right? If we picked delta equals 0.0001, then it would still be the case that whenever x minus 4 is within that range of delta, whenever x is within a distance of 0.0001 of 4, that 5x minus 9 would be within a range of 0.001 of 11. But that's right. That's fine. Once you have a value of delta, any smaller value of delta will work. If you pick a value of delta, or you find a value of delta will work for a specific value of epsilon, that same value of delta will work for any larger value of epsilon. That's the transitive property of inequality. But what we're looking for is any one that will work. And in fact, this first step is already more specific than we're generally going to want to be. Instead of looking at a particular value of epsilon and looking for a particular value of delta, generally we're going to be looking for proving that this will work for any value of epsilon, because the definition says for all epsilon greater than 0. Right? So we start by saying that we're going to pick epsilon greater than 0. Or sometimes it's written as let epsilon be greater than 0. We're not saying what value epsilon takes on. We're just saying that there is a value of epsilon greater than 0. Right? All we know about epsilon is that it is greater than 0. We can generally assume it's relatively small. All we know for sure is that it's greater than 0. And we'll consider the inequality absolute value of f of x minus L is less than epsilon. And we'll do the same game that we did before. We'll plug in our f of x, we'll plug in our L. We don't know what epsilon is now, but that's okay. So we get that the absolute value of x minus 4 is less than epsilon over 5. And that epsilon over 5, let me try writing that a little bit higher on the screen where it actually comes out legibly. That epsilon over 5 will serve as our value of delta. all of this is considered to be scratch work. It's not technically part of the proof, but it's the important part of the process of performing the proof. Right. This is where mathematics tends to become a black magic art, because in presenting this proof, if I was writing this proof out for purposes of writing a published article, I wouldn't include any of this work. After let epsilon be greater than 0, the next thing I would write down is if 0 is less than absolute value of x minus 4 is less than epsilon over 5. Because that's what the definition of limit tells us we are looking for. We're looking for x bounded by this three-piece absolute value inequality. 0 is less than x minus c is less than delta. I know what c is. I know what delta is in terms of epsilon. So whenever 0 is less than absolute value of x minus 4, less than epsilon over 5, then absolute value of 5x minus 9 minus 11 is equal to absolute value of 5x minus 20, which is equal to 5 times the absolute value of x minus 4. And by substituting in the inequality we have over here, x minus 4 is less than epsilon over 5. So 5 times x minus 4 is less than 5 times epsilon over 5, which is equal to epsilon. So we end up with, whenever 0 is less than x minus c is less than delta, f of x minus L is less than epsilon, which is exactly what the definition of a limit says. So this is the part that actually proves the statement. The first half is the scratch work. The second half is the actual proof. Let's look at a more challenging example. The limit as x approaches 2 of x squared plus 4x plus 7 is equal to 19. Similar to what I said on the first example, we know that polynomials are well behaved, so you should just be able to evaluate, and anything that should work nicely will work nicely for a polynomial. You plug in x equals 2. 2 squared is 4. 4 times 2 is 8. 4 plus 8 plus 7 is 19. So it looks like this should work. But if I want to prove it, I start by letting epsilon be greater than 0. And I consider what would happen if I took the absolute value of f of x minus L and set it less than epsilon. All right, the process of the proof is going to give me that x squared plus 4x plus 7 minus 19 is less than epsilon, which will simplify into x squared plus 4x minus 12. And that does factor. It's a little bit more cumbersome to factor than the linear one, but this is a quadratic that factors. We need two numbers that multiply to negative 12 and add to positive 4, like positive 6 and negative 2. right? The absolute value of the product of two numbers is the same thing as the product of the absolute value of those two numbers. So I can split that up as the absolute value of x plus 6 times the absolute value of x minus 2 is less than epsilon. Now, this isn't quite as convenient as what we came up with last time. So we're going to have to do a little bit more work, right? If we could get this absolute value of x minus 2 by itself, that would give us the value of delta. So our goal is to find some sort of a bounds on the absolute value of x plus 6. The traditional way of doing that is to assume that delta is less than 1. Right? As I was saying at the beginning of this video, we're looking for a value of delta that satisfies the definition, not the biggest value of delta that satisfies the definition. So if it turns out that we could have chosen delta equals 37, well, anything smaller than 37 would also work. So worst case scenario, we're saying, even if we come up with something that would be bigger, we know we could pick delta equals 1, but we're probably safe in assuming that delta is going to end up smaller than that. Because if epsilon is a very small number, delta is going to be usually a smaller number. Sometimes a slightly larger number, but something in that regard. All right, that is a delta, not an 8. All right, if we assume that delta is less than 1, then the inequality 0 less than absolute value of x minus 2 less than delta is satisfied whenever the absolute value of x minus 2 is less than 1, or whenever the first inequality is satisfied, the second one is also satisfied. There are conditions that would satisfy the second that wouldn't satisfy the first, but every condition that satisfies the first will also satisfy the second, and that's good enough for us for right now. I can solve this absolute value inequality if I'm using a pen and not an eraser. I can see that x has to be somewhere between 1 and 3. Right, now going back, I'm looking for something to do with this absolute value of x plus 6. So in order to force this to look like x plus 6, I can add 6 to all three sides of this inequality. It seems like a stupid thing to do, but it's a thing I can do, and that's what's important. So x plus 6 is somewhere between 7 and 9. All right. At this point, we're going to take whichever side is bigger in absolute value. Right? In this case, the 7 on the left is a smaller number, but also smaller in absolute value. If it had turned out that both of these numbers were negative, we'd be looking for the more negative value. But whenever x plus 6 is between 7 and 9, it is also true that x plus 6 is less than 9. Right? There are values that satisfy this new inequality that don't satisfy the old one, but every value of x that satisfies the old one also satisfies the new one, and that's what's important. Because not only that, but if x plus 6 is less than 9, then the absolute value of x plus 6 can be less than 9, or I guess whenever x plus 6 is between 7 and 9, then the absolute value of x plus 6 must also be less than 9. Right? Taking that back up here to that inequality that's almost gone off the top of the page at this point. We have that the absolute value of x plus 6 times the absolute value of x minus 2, we want to be less than epsilon. Now we know that the absolute value of x plus 6 times the absolute value of x plus 2 is less than 9 times the absolute value of x minus 2. So if we set that less than epsilon instead, then we'll be assured that everything will work, and we get that we want the absolute value of x minus 2 to be less than epsilon over 9. All right, let me stress one more time. I've done it several points throughout this exercise. I have done things where in satisfying the new condition, or in satisfying the old condition, we can be guaranteed to satisfy the new condition as well. But in satisfying the new condition, we cannot be guaranteed to satisfy the old condition. That's okay. All right. This is something slightly different than solving an inequality that you are accustomed to. We're not looking to find the value of x. We're looking to find a convenient bounds on x, not the best one, which is weird and different. So I've made several steps here that cannot be unmade. They work in one direction, they don't work in the other direction, which is not normal in algebra, but perfectly okay for us in calculus. All right. So once again, all of that is scratch work. That's all the stuff you do on the side of the page. That doesn't go in the proof, although I do suggest writing it out if you're trying to prove something for class. If you're typing this up as a published result, none of that gets put in the proof. That's scratch work that goes along with the proof. So after the statement, let epsilon be greater than 0, we say whenever 0 is less than absolute value of x minus 2 is less than epsilon over 9, and 0 is less than absolute value of x minus 2 is less than 1. Again, remember, because we said that delta had to be something smaller than 1. So as long as we satisfy both of these, we will pick whichever one of epsilon over 9 or 1 is the smaller value, and then we'll be guaranteed to satisfy the other one. I don't have to say which one is our value of delta. It will work out. That's what matters. But whenever this happens, if I consider the absolute value of f of x, which was, I'll remind you, x squared plus 4x plus 7 minus L, which was 19. Well, that's equal to the absolute value of x squared plus 4x minus 12. And that factors, like we did before, into absolute value of x plus 6 times absolute value of x minus 2. And we know that x plus 6 is less than 9 from what we did before. And we know that x minus 2 is less than epsilon over 9. And if you multiply those two things together, you get epsilon. So whenever absolute value of x minus 2 is between 0 and either epsilon over 9 or 1, whichever one is smaller, we get that the absolute value of f of x minus L is less than epsilon, which is exactly what the definition of the limit tells us is supposed to happen. Okay. A little bit lengthy, but we got through it. Hopefully everything makes sense there. All right. And with that, here is one for you to play around with. I'd like you to use the epsilon delta definition of limits to prove that the limit as x approaches 5 of 3x minus 9 is equal to 6. Take a few minutes, see what you can do with this one, and I'll see you in the next video.